Morning.
Right, yeah. Okay, guys. Um, Before we start, does anybody have any questions at the moment?
No.
Did you guys receive the email yesterday or emails? Okay, so I guess we may be looking forward to a super long weekend. Okay. Please be aware that you're off on President's Day as well, okay? Okay, guys. Then let's look on a little bit, yes, okay, abstract topic. Which is primarily going to be yes, okay. Harmonics. Clear, okay. Now please keep in mind, guys, okay, from harmonics, what that will lead to is what we will call harmonic imaging. Okay, so what harmonics are going to do is they're going to produce what we will call harmonics or harmonic imaging. But first of all, let's say, okay, what is harmonics? Now, guys, what we know is that, for instance, okay, if we, for instance, had a transducer. Yeah, okay. Now this transducer here is okay, it had a frequency. Okay. Now to begin with, we refer to this frequency as the frequency. Clear? Okay. Later on, in later chapters, we as okay refer to this frequency as the main frequency, or we could also call it the resonant frequency. Clear? Did that make sense?
Yes.
Okay. Now, what we mainly are going to do now is, okay, as this is now going to, as okay, or mainly as okay in context to harmonics, we're just going to, as okay, refer this to as a fundamental frequency. Okay, so in this chapter here, as okay, you see the word fundamental frequency. What that still would mean is, okay, as what in the previous chapters was referred to as the main frequency, which we also as okay call the fundamental or the resonant frequency. In this chapter here, we may just for a brief while explaining as okay what harmonics mainly are going to be is going to be as okay we'll call it a fundamental frequency. Clear? Okay, not your bandwidth. Clear? Okay, not your bandwidth, because your bandwidth that will mean is okay that's the range between the minimum and maximum, because it's okay the difference between the minimum and maximum frequency. But somewhere in between those two frequencies that we have occurs the main frequency of that transducer, which we also refer to as the resonant frequency, or which we in this chapter here will call a fundamental frequency. Did you guys get that?
Yes.
Okay, so when we first is okay, use this transducer, it's okay, where it was using its fundamental frequency, main frequency, resonant frequency, that was going to give us okay as because that's okay. Let's just say it's okay, a regular image. Okay, now what is going to just okay produce harmonic imaging? Okay, for that we mainly as okay, we can yes okay, we can produce it yes okay. For harmonic imaging. Okay, what we need is harmonic frequency. Clear, okay? Now your question is going to be yes, okay, where would that harmonic frequency come from? Well, the frequency is still going to yes, okay, be produced by the transducer. Okay, or we can say that okay, the transducer main, yes, okay, is still going to produce main frequency, resonant frequency, and or fundamental frequency. But what this frequency is okay is going to do is going to just okay undergo some changes. And actually this okay will become a harmonic frequency. And as a result of that harmonic frequency, the kind of imaging that we will get is going to be as okay harmonic imaging or harmonic images. Did that make sense? Okay. Now, what we may talk a little bit more in detail about later is, okay, how is it that this fundamental frequency here become a harmonic frequency? Okay. But the simple formula of remain is okay, remembering so what is a harmonic frequency related to a fundamental frequency is that the harmonic frequency is always going to be twice that of your fundamental frequency. Clear? Okay, so we can straight up say that okay, where were we? That the harmonic frequency is going to be equal to, that's okay, what we call the fundamental frequency. Okay, double. Did you guys get that?
Yeah.
Right, okay. So the basic thing is, let's say it's okay that we had a frequency or we had a transducer with a main frequency, a resonant frequency, or what we in this case are called fundamental frequency of, let's say it's okay, 5 megahertz. Clear, okay. And they ask yes, okay, this transducer here is okay. Our transducer produces a frequency of, or has a frequency of 5 megahertz. What is going to be the harmonic frequency? Well, okay, not really rocket science. I hope everybody will be able to say, okay, double a number. So he says, okay, and 5 megahertz was the fundamental frequency, then the harmonic frequency for this transducer is going to be 10 megahertz. And what this 10 megahertz frequency here is going to lead to is it's going to produce a harmonic image. Did you guys get that?
Yes.
Okay. Some of you will say that what if the frequency of the transducer was 3 megahertz? Well, okay, as for this transducer here, so okay, it's going to be the same. Sorry. 3 megahertz. And you double that, and okay, yes, our harmonic frequency is then going to be 6 megahertz. Okay. Was the fundamental frequency 6 megahertz? Well, okay, yes, you just double that. And okay, your fundamental frequency or your harmonic frequency then going to be 12 megahertz. Clear? Okay. But what these harmonic frequency here is, okay, whatever they were, which was made as, okay, that's twice the fundamental frequency, is going to do the kind of images that they will produce will be referred to as harmonics images. Did you guys get that?
Yep.
Yep.
Okay, so that was not really rocket science this far, but okay. Okay, whatever the transducer's frequency is, double that, that will be the harmonic frequency. Clear? Okay, and that will be the frequency that your system will use to produce what you call a harmonic imaging. Clear? Okay, now is this a function that we could turn on and off? Yes. If you guys remember the other day on the keyboard, I showed you a knob that says, or a button that said harmonics. Clear? Right? Okay. And pretty much, okay, as by turning that on, the message that you convey to the system is that you want to just, okay, create a harmonic image. Did you guys get that? Okay. Now, some of you will be scratching your heads and say, well, okay, well, what is wrong with a regular image? There may be nothing wrong with it. So if there's nothing wrong with it, yes, okay, you may not need to, yes, okay, create a harmonic image. But yes, okay, the harmonic images come with some benefits. Or we can say it's okay, has certain advantages, or you can say superiority upon regular scans. Clear? Okay. And that's pretty much okay as one of the main things that we will be looking at when we talk harmonics. Any questions so far? Okay. So what we so far have called just okay, main frequency, what we call the resonant frequency in this chapter here, just to explain it's okay what a harmonic frequency is going to be. We will refer to that frequency as the fundamental frequency. Okay, that being doubled, that becomes your harmonic frequency. What will that lead to? The production of harmonic images. Did you guys get that?
Yes.
Good. Yep. Now, besides that, if that was it in harmonics, then okay, yes. But harmonics, actually, yes, okay. or we can say it's okay, harmonics. Now we may just okay, just said okay, one of the criteria or one of the characteristics was that it was twice. I was like, your fundamental frequency. Yeah, okay. Whereas okay, as in fundamental, yes, okay, it was fundamental. Okay. If the transducer, yes, okay, produce, let's say, yes, okay, 2 megahertz during transmission, we will say, yes, okay, oh, sorry, transmission. We could say, yes, okay, that the frequency of sound at reception was also going to be 2 megahertz. Yeah, okay, so that's how, and okay, what we will get from that was going to be, is okay, because that's okay, a fundamental image or regular image. Now, another characteristic, and pretty much okay, yes, one that we're going to just okay, be as okay, sticking along a lot onto while describing yes, okay, what is it that harmonics actually does or how is that harmonics they display what we'll call a non-linear behavior. Whereas okay, in fundamental imaging, we mainly yes, okay, have a because it's okay, linear behavior. So harmonics mainly yes, okay, display what we will call a non-linear behavior. Is that clear? Did you guys get that?
Yep.
Good. The next thing is going to be that we mainly will say that, okay, yes, harmonics, that is going to be, yes, okay, you can either say it's okay, we can say it's okay, free from distortion. Or some people, it's okay, may just put it as distortion free. Whereas, okay, in our fundamental imaging or regular imaging, it's okay, you will have some sort of distortion. Okay. Now just to yes, okay, get clear about it's okay, what in the is it that we mean by distortion? Clear, okay. Which we then don't see in case of harmonic imaging or harmonics, because it's going to be free from distortion. So let's just say it's okay, or let's just get clear about what we meant by this distortion here. So distortion, what is that? That's going to be as okay, a form of loss of energy. And where can that loss of energy happen? In the pulse and beam. Did that make sense? Now, especially as okay, when we talked about the beam, what is that this distortion here is going to lead to, or what was it that distortion was going to lead to? Loops, right? Right? Wasn't that what we call loops? The energy was able to escape from the main course of the beam. Did you guys get that?
Yep.
Right. Okay. So what is it we can see is one of the main benefits of, okay, it's harmonic imaging. If you don't have distortion, if you don't have loss of that energy, there will be no loops, and the artifacts produced by loops will not be present or will not be there in a harmonic image. Did you guys get that? Okay, so one of you can say is, okay, one of the main benefits is that it is going to minimize, or let's say, okay, reduce the production of artifacts. And what are artifacts? That's going to just, okay, mainly is, okay, affect your accuracy of your image. Okay. So mainly as, okay, three major things that you guys will need to just, okay, know about or remember about harmonics. First, produced by harmonic frequency. What was a harmonic frequency? Twice your fundamental frequency, also known as main frequency, also known as resonant frequency. Clear? Second is that, okay, as harmonics, what they do is, okay, they have a non-linear behavior. Clear? Third is that, okay, yes, they're going to be distortion free. Clear? Okay, they're going to be distortion free or free from distortion. What was distortion? A form of loss of energy from your sound beam or pulse. Any questions? Now you may say, does that mean that the sound wave doesn't attenuate? No, it will still attenuate. Okay. Okay. That's not distortion. That is still going to happen. Okay. But things such as, okay, loops, etc., that is going to be what we don't see being produced in harmonic or harmonics, as far as, okay, due to harmonic frequencies, which produce what we'll call a harmonic image. Okay, guys. Now, in this chapter here, or mainly it's okay, what we may talk about is, it's okay that we have, that's okay, we can have, it's okay, two types of harmonics. And ladies and the gentlemen, or dear students, okay, when we are going to, yes, okay, talk about, yes, okay, these two type of harmonics, yes, okay, the main thing that is, okay, we'll be stuck on is going to, yes, okay, that are those non-linear behaviors that they display. But the two types of harmonics is respectively, oops, sorry. tissue harmonics. The second one is going to be contrast harmonics. Okay. Now, just to begin with, guys, please remember that tissue harmonics, and especially as these non-linear behaviors that we will talk about, that's that they develop during transmission. Yeah, okay. So what is going to become is what we'll call tissue harmonics will produce a harmonic image. Especially as these non-linear behaviors that we see in tissue harmonics, they are mainly as going to develop during transmission. Now, what do you mean by develop? We can mean it as that they are produced as the sound wave produced by the transducer is in the phase of transmission. As it travels from transducer in the tissues. Or we can say, away from the transducer. It's going to be during that phase of the journey of the sound wave that the type of harmonics that will develop will be what we call tissue harmonics. Okay, now the cheat here is, guys, some things have a cheat. Tissue is T, transmission is T. So you just have to remember that, tissue harmonics is they develop during transmission. Okay, the main thing that we will talk about that actually is the causes or it leads to is what we will call harmonics as a harmonic frequency, which is going to be twice of that. Okay, which will then create as what we can call as a harmonic image. Okay, but those harmonics that we refer to as tissue harmonics develop during the transmission. Okay, guys. Now, contrast harmonics. Okay, now that's probably not something that as we practically perform in the school. Okay, why? Because for contrast harmonics, what we will be needing is contrast agents. Clear? Okay, and what are those contrast agents? Those are mainly going to be drugs that the patient may have to consume, or they may give that in the form of a injection. Okay, did that make sense? But with help of that contrast agent, mainly because the interaction between the sound wave and contrast agent is going to have that nonlinear behavior. There are going to be some nonlinear behaviors in the interaction between the sound wave and the contrast agent. So that's why we call it contrast harmonics. Clear? Okay. Okay. But this contrast harmonics, our question, or the first point is, okay, yes, where is it or when is it that develops? So that's okay. That develops during reception. Or let's say it's okay, reflection is probably a better word. And what is the reflection going to be? What do you mean by reflection? That's actually is okay when those sound waves are returning back from the tissues, or in this case, it's okay, most likely it's okay, the contrast agent. Okay. But it's just okay as those sound waves that have hit the contrast agent return back, that's the reflection. It's during that phase that your contrast harmonics develop. Is that clear? Now, why do we still call it as okay harmonics? The reason that we still call it harmonics is that okay, yes, there's going to be as okay a nonlinear behavior as a result of the interaction between the sound wave and the contrast agent. Okay, so before talking about it, okay, contrast harmonics, we will have a brief talk about what the blue is that a contrast agent is. Okay, if any of you ever had gone for us, okay, a CAT scan, an MRI, or so and so and so, in some cases they may give you okay something to drink, some chalky solution. Yucky.
It's actually not chalky anymore. It's more like water.
It depends upon it's okay what they want to. But okay, before, well, okay, they may still be you. Okay, it depends, my dear. Okay, what they want, okay, what kind of substance they give it to you. Okay, what the goal is. But they may also just okay give you an injection right before the scan. So that's okay. It can be as okay administered in different ways. Now, my dear, you are allowed to just okay practice HIPAA. You don't have to declare. But if you don't want to, you can say, okay, I just want to not use my First Amendment rights. Now that chalky system, that chalky substance, my dear, that's more like okay, if they want to just okay scan your gut, things like stomach, intestine, and so on, so on, so. But yes, okay, there are substances that they can give, and okay, yes, it may be watery rather than giving you an injection. Okay. Now, some of these contrast agents themselves may be radioactive. Especially, it's okay, contrast agents for thyroid scans and so on. So, yeah, okay. But peace be with that. So, any questions so far about regular versus harmonics? Okay, so any image that's okay, which is produced as a result of harmonics frequencies, which is twice that of a fundamental frequency, will be considered a harmonic image. Clear? Okay, so that was one thing. The second thing was that, okay, all harmonics are displaying a nonlinear behavior. Clear? Third is that we can say that, okay, yes, harmonics are distortion free. Okay, which mainly means, okay, not going to have loss of energy of the pulse and or the beam. Which mainly will mean that, okay, your harmonics are going to mainly be produced by or require strong signals to produce harmonics. Okay, so it's mainly going to be strong signals that will produce your harmonic images. Did you guys get that? Good. Any questions?
No.
And last but not the least, well, okay, the two kinds of harmonics that we as okay may end up talking about is going to be tissue harmonics. Okay. Tissue harmonics, that's okay. Why do we call them harmonics? Mainly because it's okay, display nonlinear behaviors. And those nonlinear behaviors mainly as okay are going to as okay further will develop during the transmission. Transmission of what? Transmission of the sound waves. The other kind of okay as harmonics, which we call contrast harmonics. Okay. Now what we may require for that is going to be as okay contrast agents. Okay. But those harmonics, now why do we call it harmonics? Mainly because that there's still going to be as okay a non-linear behavior in the interaction between as okay the sound waves and the contrast agent. Okay, and what that will produce is going to be as okay, or ultimately as okay, we'll call contrast harmonics. But those contrast harmonics, as okay, they develop during reflection. Okay. So the Chi tissue harmonics, yes, okay, develops during transmission. Chi. Okay, guys. Now, if you for instance, okay, just no need to, for instance, okay, chalk off a non-linear behavior. Now, before we go and talk about, okay, what the a non-linear behavior is, let us just, that's okay, try to clarify that, okay, as what do you mean by linear behavior? Now, guys, a simple example of, yes, okay, how to explain what a linear behavior is versus, let's say, it's okay, non-linear behavior. is okay, yes, if you, for instance, okay, draw a graph between, yes, okay, of two things that are related to one another. Clear? Now we may say here, yes, okay. For instance, if you, for instance, okay, say A and B. Now what we just can say in that case, yes, okay, that A and B are directly proportional, which may literally mean that as A increases, for instance, okay, B will also increase. And if that was okay as not only an increase like that, but actually that's okay, also that's okay, had a linear increase. Well, okay, yes, our line will be like this. Even if you, for instance, say that, okay, as A and B, for instance, even as okay, if they were inversely proportional, sorry. That could still be, yes, okay, that could still be a linear behavior. Okay. That we say that, okay, yes, well, what does that mean? That as, for instance, in this case is okay, that A decreases, B will increase. Okay, so that would have been a line like this. Clear? Okay. Or even if we say that, okay, yes, as A increases, so it's okay, let's say it's okay, A is constant, but B is okay, in this case is okay. Let's say, yes, okay, may increase. Because that's okay, it stays at this, but the value of B increases. But what you mainly see is okay that all in this case, all these three cases of what did we have? Straight lines. So these media, okay, said that okay, is that the relation between A and B displayed a linear behavior. Did you guys get that?
Yep.
Okay. Whereas, okay, yes, a nonlinear behavior. Okay. Now we can still say that, okay, yes, A and B, for instance, okay, A and B is okay. Well, it may not be appropriate to say that. Okay. Okay, yes, they still be compared against one another, but it's okay that they have a non-linear relationship. Right. So that non-linear relationship is okay. If we draw that, it's going to be as okay. We can say, okay, they may start at the same, but okay, yes. Something like this. Clear, okay. So that's going to be a non-linear relationship. We can say it's okay that it is not going to be proportionate. So that's why it's okay, a non-linear relationship or a non-linear behavior also is going to be as okay, this proportional. Or if we look at the outline of this line here, it is not straight as it was. in linear behavior. So that's going to be that it actually is okay, is irregular. Okay. So mainly as okay, due to this nonlinear behavior, as okay, what it actually makes the nonlinear behavior to become is that it is unpredictable. Okay. Because that's okay. As you find that's okay, going up, you don't know that's okay when it will flip around and go down. And for how long is it will descend? Clear, okay. Okay. You can't say just because it's okay, it reached the peak here at this point is going to just okay do the same over here as well. No, you saw it. It went taller. Okay. You can even say it's okay that's okay. It's at some point it's okay, may go so long down. Okay. So you really is okay, won't be able to say, well, okay, but I kept on increasing, so it's going to keep on increasing. I kept on decreasing, so it's going to yes, okay, straight decrease. Well, okay, yes, it just remains solid. That's okay. This remained the same while okay, the other means okay, just increased, but there was a steady relationship between yes, okay, the changes in factor A and B, A and B, A and B. That's not what you can say here. Just like, yes, okay, if you work now, what are the two kind of ways that you can get paid? Yes, guys, if you work, what are the two major kind of ways that you can get paid?
By check or by direct deposit.
Okay, but in both cases, money comes to your account, right? We're talking about the salary. Okay, you may as okay have a fixed salary. Most managers and things like that, it's a fixed salary, whether they work 40 hours a week or 2 hours a week, they get that fixed salary, right? Clear? Okay. Some people, yes, okay, may get paid by the hour. So you can say, okay, the more hours you work, the more you're going to be able to scrape in. Did that make sense? Clear? Okay. So that's okay. At times when you work more hours, your graph goes up. And then there will be times when you don't work that many hours, that's okay, your graph goes down. Clear? Okay. So you can't say that, okay, my pay is having a linear behavior straight because I get paid a fixed amount no matter how many hours I work. Clear? But generally speaking, yes, okay, what we just can say is that a linear behavior, that okay, yes, if you want, yes, okay, relate two factors to one another and they display a linear behavior, yes, okay. It could either be, yes, okay, if they were directly proportional, if they were inversely proportional, or you can say, yes, okay, here's okay, the value of A may, yes, okay, remains the same, although it's okay, B may be, yes, okay, steadily increasing. Or what we see in all these cases, okay, that these were relationships where the okay, it displayed a linear behavior because there were no ups and downs. Clear in your line. So that's okay. We can actually, oh shit, sorry. Oh no, what I meant to do, sorry. So just yes, okay. Because like what is a nonlinear behavior? If there are ups and downs. So how is life? Look at your life for as long as you can remember. Had it been straight like this? No, there are always going to be ups and downs. Okay. That's why it's okay. It's a bumpy ride. Clear? After many years of okay, bumpy rides, that's okay. You may say, okay, now I'm set. I got my house, I got my car. Well, okay, that's a big achievement. You got okay, yeah, okay, I got a job, okay, it's okay, the hours are good. I can make ends meet together, I can get vacation time, whatever. And not go bankrupt. So, okay, now I can say, okay, as after all the non-linear behavior, now it's more smooth, right? Yeah, okay. But just to remember, as okay, what non-linear behavior is, that is going to be up and down. And you may not predict for how long it's going to go up and at what point it is going to be down. And then it's okay, how far down is it that it's going to go? We thought that winter was over, right? Did somebody have fun yesterday plowing the snow? Right, okay. So yes, okay, ups and downs. Okay, so those ups and downs, yes, okay, that is a non-linear behavior. Any questions, guys? Good. And yes, these are major point of our harmonics. It's going to be yes, okay, these nonlinear behaviors that they display. That's the main point that we will be talking about as we proceed through this chapter. Now, sorry guys, please remember that, okay, yes, there was it. This harmonic frequency. This harmonic frequency here is okay, may also be called the second harmonics. Okay, now let's do it this way. Harmonic frequency is also known as second harmonics. Now, just a cheat to remember, it's okay that it's also called second harmonics because it was, what was it? Why is your fundamental? Okay, it was going to be twice the fundamental frequency. Okay, guys, now just take a short, should we say, 15 minutes. Yeah, 15 minutes break. Now, please read on, yes, okay, these first 3 pages. Okay. And when we come back, yes, okay, we will start talking about our harmonics or tissue harmonics. Yep, okay. Does that sound fair? Okay, good. Okay, guys. So our first topic is going to be tissue harmonics. Yeah, okay. And as we just said earlier, that this develops during transmission. Yeah, okay. We also said that they will be displaying nonlinear behaviors. And it's mainly going to be as okay, these nonlinear behaviors that we will be talking more about. But last but not the least was that we said that okay, yes, that they were also distortion free. Okay. But what these tissue, what this harmonics here is okay will do, will lead to is okay what we call harmonic images or harmonic imaging. What did we mean by this harmonics? Mainly was that it was going to be twice the fundamental frequency. Did you guys get that?
Yep.
Good. Now, guys, when talking of okay as tissue harmonics, and as we see as okay developed during transmission. Okay, now we can mainly as okay look at that in 2 ways. Or it's going to be as okay two major, we can say as okay features of the sound wave that will be displaying nonlinear behavior. Okay, which will produce just okay, which end up creating what we can call as okay a harmonic image. That's okay, we can say it's okay, the non-linear behavior of tissue harmonics. Now, guys, the first one is going to be that there's going to be is okay a nonlinear behavior when we talk about rarefaction and compression. Well, let's just change the colors. So, Let's see if you go to compression first. Versus that's okay. Now I hope that you guys remember what that was. Because what we meant by rarefaction or compression was that when particles were close to one another, right? Okay. That's fine. Sorry, guys. Rarefaction, we meant that, okay, those same particles, for instance, okay, were farther away from one another. And what we mainly will actually is okay as a result of rarefaction and compression, there actually is okay going to be a non-linear behavior being displayed in the propagation speed. Clear? Okay. Now, what we mainly will see in compression is that there's going to be as okay a greater particle motion. Now, pretty much okay, due to that greater particle motion, we will mainly see that there's going to be a greater pressure. Okay. And maybe it's okay because particles are closer to one another, that's okay. You will have a greater density. Whereas the opposite is just going to be, it's okay, what we see in what you want to call it, your rarefaction. That will be as okay, lesser particle motion. Lesser pressure. And likewise, okay, as a lesser density. But even in that, with that said, what we mainly will see that, okay, as during compression, there will be as okay, a greater speed of sound. Or you can say it's okay, that the sound actually is okay, will travel during with a greater speed versus it's okay in rarefaction, that's okay with okay, there will be a lower speed of propagation speed of sound. That makes sense. And pretty much okay is okay due to this being greater, this being lesser during the two different stages. That's why we can say it's okay that the speed of sound is not going to be as okay a straight line like this, but we can say rather up and down. Up, then down. Up, and then down. Okay, so due to these ups and the downs, we can actually say that that's going to be okay, a non-linear behavior in the propagation speed of sound whether it's okay, all depend upon whether the particles were compressed or rarefied. Now, what we also, what I briefly also mentioned during, when we talked about compression and rarefaction, I mainly said, during compression, that's actually where the sound wave will have greater power, and due to that greater power, greater intensity, and amplitude, which is going to be where these as well are going to be lower during rarefaction. Because what was power? The rate at which energy was transmitted from particle to particle. So that would be greater here. And due to that greater power, we will have a greater intensity. Did you guys get that? And likewise, over here, you can say mainly because of the greater distance between the particles, there's going to be a lesser amount of energy that can be transmitted from this particle to this. And that would mean what we call power. You mainly call that in this phase here, the sound wave is going to have a lesser intensity, and nuclear that's a lesser amplitude. Did you guys get that? Okay, so all is okay. It was not smooth like that, but rather tick, 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 tick. Ups and downs, ups and downs, ups and downs. And what do we call that ups and downs? Not the bumpy ride on the road, but yes, a nonlinear behavior. Clear? Okay. So that was, we can say as characters or nonlinear behavior, number one. Okay. But what we actually will also say is or as we said earlier, that is this develops during transmission. So what we mainly mean by that is that difference between what happens during compression and what happens during rarefaction. One is using harmonics is going to become greater and greater and greater. Clear? Okay. So not necessarily like this, but if we said, that this, for instance, here was a nonlinear behavior, we can see that, yes, if for instance, this was the up, and let's say it's if we begin with this was the down. Yeah. Did that make sense?
Yes.
Yeah.
Okay, so you can say it's okay, of course, that's okay. This is not a non-linear, this is not a linear behavior. But the main thing is that, okay, we mainly as okay say that, well, okay, as there may be further as okay development of power, intensity, and amplitude, which means as okay, will just all be as okay. You can say translate it into as okay. In this case, is okay the strength of the sound. So as we see as okay, as the sound propagates deeper and deeper and deeper and deeper, its strength is going to, yes, okay, increase. Okay. Yeah. So that means, okay, that explains what we mean by saying that, okay, yes, tissue harmonics develops during transmission. Okay. But what, okay. So here we actually would say that, okay, yes, during compression, well, okay, yes, we will, yes, okay, not only will we have, okay, yes, a greater speed than what we had during rarefaction. By using as, okay, these variables here would be greater during compression and lesser during rarefaction. Where more energy mainly as okay will be transmitted during compression compared to rarefaction, which means okay makes it a non-linear behavior. Any questions about that?
No.
Good. Now, guys, please keep in mind that rarefaction and compression is also going to be as okay brought back into the discussion when we talk of the nonlinear behavior of contrast harmonics. Clear? Okay. Pretty much okay as the main and only as okay nonlinear behavior in contrast harmonics is going to be referring to is okay compression and rarefaction. Clear? Okay, which will produce your contrast harmonics. Just so you guys are aware of that. Clear, guys? Now the real point about yes, okay, harmonics that we say that okay, yes. Now just keep in mind, guys. We say that okay, yes. Or we always say this okay, that okay, it develops during the transmission. Clear? Okay. Now, guys, there is a figure in your book. And we mainly says, okay, figure 17.6. Do you guys see this?
Yeah.
Good. Okay. Now, this figure 16 or 17.6 is made as okay, just a graphical display of okay as your tissue harmonics. Actually, as okay, image effect of the tissue harmonics in terms of just okay, how that actually is okay will affect your image is shown in figure 17.7. where you mean yes, okay, I have two images on top of one another, right? Okay. First, we have, okay, a regular fundamental image, where, okay, the bottom one is going to be, yes, okay, a harmonic image. What did we mean by a fundamental image? That it was made as, okay, produced by a regular main fundamental frequency or main frequency or resonant frequency. Okay, whereas when we say, okay, a harmonic image, that was because it used a harmonic frequency. Okay. Now, one thing that we said about is, okay, that it is displaying a non-linear behavior. Yep. Okay. So tissue harmonics is, okay, it develops during transmission, which means to me that, okay, as the sound waves are being transmitted, yes, okay, your harmonics may increase. But with that, we also say, yes, okay, not only that nonlinear behavior, but it is also going to be, yes, okay, unpredictable. Yeah, okay. And or yes, okay, another way of, okay, looking at your non-linear. Okay. That doesn't mean that, okay, yes, that once it's on the rise, it's going to just, okay, keep on rising. Because that's going, it's okay, because it is unpredictable. So that's going to be, it's okay, a point where there's going to be a, it's okay, abrupt decrease in your harmonics. Did you guys get that?
Yes.
Okay. So that's pretty much, okay, as what we will be looking at when talking this figure here. But then also says, okay, how is it that, okay, as it actually is, okay, affects, or we can say, it's okay, may cause that, okay, as our harmonic image is somehow as, okay, improved. Because why else would we as, okay, develop a certain technology if it couldn't lead to an improvement? If it was going to, as, okay, further degrade, you can say, as, okay, the quality of your image, the accuracy of your image, then why even bother? Yeah, okay. Now, guys, just look here. Okay, now this is mainly as, okay, just, okay, it's a reproduction of 17.6. Where again says, okay, now, okay, we have two axes. Okay, now what they mainly is, okay, just did along the y-axis is, okay, that this is, okay, harmonics, strength. Now, if you look from here, yes, okay, you would know, yes, okay, what we mean by the harmonic strength. Things like the power, intensity, and or amplitude. Okay, which, as we said, okay, when looking at, okay, the phases of cycle, or okay, phases of, okay, as are related to, as, okay, the distance between the particles as the sound was propagating, was, okay, compression and rarefaction. But we mainly, as, okay, also say that, okay, as this strength here that develops during transmission. Oops. Okay, so what we can say is, okay, briefly is, okay, we can say, okay, develops during transmission. But even yes, okay, this development here is now going to have a non-linear behavior. Okay, which mainly will mean that, okay, yes, it will not be straight like this. So this case is okay, is going to yes, okay, had there been a linear behavior between yes, okay, the strength of the harmonics related to depth of image. Or let's say it's okay, just the depth. Did you guys get that?
Yes.
Did you got okay? Okay. So of course, yes, okay, we can say it's okay as we go here. That mainly just mean that okay, yes, we are talking about deeper and 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 deeper areas, or just okay, depths of the image. Okay. Which okay, as if you looked at an image, we can mainly say as okay, this will be as okay, the increasing depth of your image. Did you guys get that?
Yep.
Clear? Okay. Now, had we, for instance, okay, had there been okay as a linear behavior, okay, where it was like this. Now, most likely, as okay, in imaging, yes, okay, on regular imaging, it would have been something like this, okay, because okay, we know that okay, as we go deeper and deeper and deeper, yes, okay, the intensity of the sound wave is going to, or the strength, power, intensity, and things like that is going to, yes, okay, decrease. But okay, yes, because that's okay, if that would have been linear. Okay, so the blue lines are going to be, yes, okay, what do we mean by linear? But we know that harmonics is okay. The reason that we call them harmonics is that they display a non-linear behavior. Okay, we even said that okay, yes, that harmonics, which we call tissue harmonics, develops during transmission. Clear? Okay. But even that development, guys, is going to, yes, okay, display a nonlinear behavior. Now, what we mainly mean by develops is that, okay, yes, it will increase as we go deeper and deeper and deeper. But where this nonlinear behavior here also is going to be what we can call is okay, unpredictable. Okay, guys. Now, what they mainly say is that at very superficial depths, for instance, clear, okay, or at shallow depths, the strength of the harmonic is pretty much, you can say it's okay, almost close to zero. Because okay, has not developed yet. Did you guys get that? So at shallow depth, what do we say here? Is okay, there is no harmonics. Or we can say it's okay, at these shallow depths here, it's okay, the strength of the harmonics has not developed yet. Did you guys get that?
Yes.
Okay. Then here, let's see at this depth here. That's where all of a sudden, yes, okay, zoom. There you say it's okay, this is where it's okay, the harmonics develops. Or we can say it's okay, at increasing depth. But what we also said was that, okay, yes, it was unpredictable. So what is that unpredictability going to be? That, okay, yes, at some point, it's going to just, okay, disappear. So yes, okay, at very deep depths, that's where it's okay. Which means it's okay that the harmonics disappears. Did you guys get that?
Yep.
Any questions?
Nope.
Good. So if you can mean, it says, okay, in this image here, whereas we can say, okay, just, okay, it will mean that it's okay, meaning this area here is okay, where we held the, we can say, okay, the benefits of our tissue harmonics. Now that main benefit, now we say, okay, first is, okay, as is going to be as, okay, distortion free. Okay, which we as, okay, we'll just talk a bit about later on. It's going to be as, okay, that there will be no lobes artifacts. Okay, but the main benefit, or the main benefit of this, okay, using harmonics is that, okay, yes, it increases the signal to noise ratio. Yeah. And what does that mean? That pretty much, okay, yes, this part of your image here is going to just, okay, be noise free. And what does that do? More signal. And what is that more signal going to give you? Is okay, we can say it's okay, a better clarity of the image. Did you guys get that? So now just look at the two pictures below, or what you see in figure 16.7. Oh, 17.7, sorry. But just look here, guys. Now this top image here, that is a fundamental image. Clear, okay? Now what you may see is, okay, that there's some haziness in this area here. Clear, okay? Or you can say, okay, the outline of, let's say, is okay, this structure. Most likely that's the gallbladder, for instance. Is not as clear as it is here. That makes sense. So what was this haziness here? That was actually noise. Yeah, okay. So what did we do? We actually just, okay, got rid of that. And you can say, it's okay, you have a more clarified or cleared out image. So isn't that good? So earplugs, earplugs, you don't hear that continuous buzzing. Did that make sense? Because okay, noise itself is okay. Is okay, yes. So that's pretty much about it. But please remind guys, very superficial structures such as okay, as your skin. Let's say as okay, even as okay, subcutaneous tissue. At those levels, that's okay, there will be no harmonics developed. Okay. Okay. That okay. But after that, yes, okay, that's when it will start develop. And okay, go bzz, like that. Okay. But just to reach the peak, and that's okay, pretty much okay, just those slightly, yes, okay, go off. So yes, okay, what we mainly can say is okay, that at superficial or shallow depths, you have no harmonics. Clear? Okay. Okay, we can say it's okay at deeper depths, that's where you will have harmonics. And at very deep depths, well, okay, as the harmonics we are looking. So that's okay. That last thing that was made is okay because that's okay because, well, okay, said that okay, that non-linear behavior was also unpredictable. Okay. But, there is an explanation for it. Okay. There is a explanation. Let me just see where they have that one. Or even, yes, okay, guys, if you look here. That's okay, just from the PowerPoints on Brightspace. But again, that's okay if you look at these two images here. Right. Okay. But this one here is okay, that was a fundamental image. No harmonics. Clear, okay. So here is okay, you don't really, yes, okay, well, okay, we can just mark it out. And it says, okay, for instance, this here is okay, no, let's just choose a brighter color, sorry. The color that stands out. You can say it's okay. This here is okay, what we mark as the liver. The main says okay, this here, for instance, okay. Okay, I marked as the aorta. Okay, but even as okay, if you compare the liver here to here, you will see it's okay, all these small dots here, what are they? Noise infested. Even the aorta, okay? Even the aorta, yes, okay. All these small dots here, what is it that they are? Noise. Okay. Now you may not be completely able to just okay, completely eliminate it, but at least that's okay. Some improvement. Okay, here you can actually see okay that okay, there is an area here, for instance, okay, this here is more, it's okay, more well defined. Over here, it's okay. Right. Okay, you as okay, these structures here, for instance, okay, here it's pretty okay mixed up. Even as okay when you look at the aorta. Right. Here it's okay, there's no noise. Because what did I say the noise actually is okay, or what was it that noise looked like? Flurries of snow or snowflakes falling down is okay across your image. Yeah, okay. You can use okay, guys, if you look here. All this area here is okay. Here you're not able to just okay see the outline of the aorta, which you still be able to just okay fall over here. Did that make sense? So what does that tell us? That it's mainly as okay at this depth here, at this area here, that we had the harmonics. Did you guys get that?
Yes.
Good. Okay. So yes, okay, as I just said, if this here was our image, and we said that okay, yes, this here is okay was graph 17.6, where we say it's okay along the x-axis, it's okay, we have the strength of the harmonics at depth. And here, both of these here is okay are zeros. Because okay, this will be a zero depth. But what we said initially was no harmonics. So in this area is okay, that was where there was no harmonics, or the strength of the harmonics was so weak. Okay, where it mainly is okay, just starts to develop or increase over these depths here. And that is going to be as okay where we have harmonics. Okay, which mainly is okay, just as okay, you know, we could have made this into a traffic light, but anyways, peace be with that. Then we say it's okay, it disappears again. Like this. Did you guys get that? So again, it's okay here again. No harmonics. Mainly because it's okay, that harmonics it's okay disappear. Yeah, okay. Now had that been okay as a linear behavior, we would have said okay, yes, it might have started developing from here and continuously non-stop or had developed. That would have been as okay, have we had a linear behavior. For me, it's okay because okay, to begin with nothing, then all of a sudden it's okay and increase, and then it's okay. So this is okay as the nonlinear behavior of the development of the strength of the harmonics. Did you guys get that?
Yeah.
Okay. Now, some of you may still be wondering, yes, okay, how in the is it that this thing here is okay happens? Now, let us just put it this way and say that, okay, yes, we had a transducer, for instance. Okay, now our transducer here is okay. Let's just say that, okay, its fundamental frequency was 4 megahertz, or 2 megahertz. Let's do that. Let's say it's okay, we had a fundamental frequency, and we said, okay, yes, that was 2 megahertz. Okay. Now that's okay. That will travel through the tissues. Now, what it may be doing, or what it will be doing, is it will be reflecting back different frequencies. Frequency which was going to be okay equal to that of the fundamental frequency, which will be 2 megahertz. What we're also may be doing, or will be doing, is mainly because we have the harmonics on. And this is mainly okay. What still will happen is that it reflects back frequency of, let's say, it's okay, 4 megahertz. It may even go further. It's okay, reflect back frequencies of, let's say, it's okay, 6 megahertz. And let's just okay, say it's okay, a frequency of 8 megahertz. So these are mainly okay going to be different frequencies that will be reflected back. Yeah. Now, since we in this case, yes, okay, had a fundamental frequency of 2 megahertz. But it's okay, since we have it's okay, the function of harmonics on. What the system mainly will do is eliminate or discard the recordings produced by this frequency. It will even discard as okay, the recordings produced by this frequency. And it will even as okay, discard the recordings produced by this frequency back as reflections. And use this one here, which is our harmonic frequency to produce the harmonic image. Any questions?
No?
Okay. So some of you say, what if our frequency is okay, well, the fundamental frequency was 3 megahertz. In that case, okay, it was still is okay, discarded this, it was still discarded this, but then it would have used this one here to create your harmonic image, because now this would have been your harmonic frequency. Did you guys get that? So just as we said, okay, that okay, the frequency is okay, may develop as we go deeper and deeper and deeper. So, okay. Oops, sorry, where were we? That the frequency is okay, develops, or the harmonic frequency develops as we go deeper and deeper and deeper. And we can make this okay. Too high of a frequency, or that lead to more attenuation. So you can say the reason that okay, as your harmonics may start to disappear at greater depths is that it gets attenuated. Well, yes, okay, guys, this is your explanation of your harmonics or tissue harmonics as it develops during transmission. Any questions? Any questions, guys?
No.
Okay. Now, please, I never say this, but I will say it. Please make sure that you know your figures 17.6 and 17.7, okay? Okay, guys?
Okay.
Yep.
Good. So what was it? Superficial, no harmonics. Deep harmonics, very deep, no harmonics. Did you guys get that? At superficial or shallow depths, no harmonics. Deeper depth, or deep harmonics, and deepest, no harmonics. Did you get it, or should I repeat it again?
Got it.
Got it? Good. Now, guys, when we said that harmonics are distortion free, or we also call it as, okay, be free from distortion. And what did we mean by distortion? Loss of energy. Okay. And this mainly is okay in terms of tissue harmonics is going to is okay apply to the beam. Now, guys, when we said that we had a beam, okay, now we know that, okay, yes, no matter what, yes, okay, the center of the beam that is going to be, yes, okay, where there will be, yes, okay, a max intensity. Okay, it also called that, okay, yes, at the focal point. Clear, okay. In the entire course of the beam, yes, okay, there was going to be, yes, okay, where we had the max intensity, the max power, and so prime, yes, okay, due to, yes, okay, the related or relatively, yes, okay, smaller diameter. Now, in a standard beam, have we, for instance, okay, had this been a transducer with just one single PCT? In that case, is okay, what was it that we were seeing? That, okay, yes, we were had the production of loops in the far zone. Or what was it that these loops actually is okay was a product of? That was due to distortion. But since we said that, okay, yes, due to, yes, okay, an increased strength of your transducer, of your harmonics, that means, yes, okay, makes them distortion free. Which means to me that, okay, yes, we would not have the loops. And what these loops here also is okay will lead to what they will produce as okay, what we can call as okay, loop artifacts. But likewise, for your array or phase transducers, right? Okay. Which we mean is okay, says okay that we have multiple PCTs. Now these is okay, what would they have? That's okay, we will have grating loops. Okay, and where did we find grating loops? Yes, okay, pretty much okay, yes. in both the near zone and far zone. Okay, but because of harmonics, it's okay being distortion free. We will not have that distortion or loss of energy is okay from the beam, which produce the loops. And that means it's okay, still leads to that's okay that there will be no loops artifact. Did you guys get that?
Yeah.
So guys, one, let's say it's okay, the major benefit of your harmonics, let's say it's okay, in this case it's okay, your tissue harmonics is that they reduce or minimize or try to eliminate is okay the production of as many types of artifacts as possible. Clear? Not only that, you can mainly say, okay, in different areas, all dependent upon is okay where your harmonics is going to be the strongest. Clear? Okay. You can actually choose that by as okay, choosing as okay the right frequency transducer. Clear? I hope you guys know the relationship between as okay frequency and transducer and penetration now. Okay, good. Clear? Okay. So, but again, yes, okay. Be able to, yes, okay, say, well, okay, at this depth here, yes, okay, that's will be, yes, okay, where our harmonic frequency will come from, which will give you, yes, okay, not only, yes, okay, a better spatial, let's put it this way, yes, okay, exit resolution, but also, yes, okay, as we saw here is okay, we talk about the loops or the absence of loops, a better lateral resolution or reduction or elimination of loop artifacts. Clear? Any questions? So if you look on page 274, your third paragraph, what does it say in bold? Beams that are likely or most likely is okay to create harmonics are least likely to create artifacts. So that's the major plus point of harmonic imaging. that you get lesser, we can say it's okay, spatial related artifacts. Or we can say it's okay, we may get better spatial resolutions. Clear? Okay. Now, please keep in mind, guys, your beam does not only give lobes out like on the sides, also up and below. Okay, so generally it's okay, your lobe artifacts. Clear? Okay. Now, any questions? So mainly, yes, okay, the nonlinear behaviors. That's the major point when we talk about our, yes, okay, harmonics. And what they did, yes, okay, they were so nice, yes, okay, give you, yes, okay, a slight summary of tissue harmonics. So what were they? Now, not present for tissue harmonics, not present as the sound leaves the transducer. What would that mean? Not present at shallow depths. Figure 17.5, right? Or 6, sorry. Okay, so we didn't have harmonics at shallow depths. Okay, they are created at deeper tissues or in deeper tissues. And that's why it says, okay, that it develops as the sound is being transmitted. Clear? Okay. But we also saw, yes, okay, that it develops at greater depths. Okay. We also said, yes, okay, it's created. Now, what they mean is, okay, just mind right here by created is, yes, okay, develops during transmission. Now, created by nonlinear speed or nonlinear behavior in the speed of sound. That was where your compression and rarefaction played a role. That there was a nonlinear behavior in the speed, all dependent upon whether your particles were rarefied or compressed. Both caused them to get rarefied. Now, two particles which were rarefied, why now will get compressed later. That okay, these two particles which now are compressed are going to be rarefied to, yes, okay, particles to which they were compressed previously. Clear? Okay. That's why, yes, okay, it's called sound waves. Clear? Okay. And mainly it's okay because those particles move like this. That's why we said that, okay, a sound wave was mechanical waves, right? Okay, so this is a chapter which is pretty much, okay, all over the place, but still not much related to any other things that we have been talking about. Okay, so sound and compression travels faster than sound and rarefaction. Okay, what I mainly told you guys. Okay, so we couldn't say that, okay, it's going to be, no, not going to be a constant speed of sound, but it's okay, compression fast, rarefaction slow, fast, slow, fast, slow. Okay, now primarily that's okay, created along the beam's main axis. And that's where it says, okay, beam's main axis or main axis. What was that? The center of the beam. Clear? Okay. Because what was it that we had there? What do we have along the beam's main axis? The center of the beam. What do we have there? The person who gives me this answer is
Is it
exempted.
lobes?
Huh?
Lobes?
Is it the highest spatial peak?
Highest spatial peak, or what do you mean by highest spatial? You are right, but can you get a little bit more specific?
Like
Your
the
answer is right.
the highest intensity is in
Highest
this.
intensity.
What am
Because
I
where is your
saying
main axis of your beam?
in the center?
In the center. Okay, I guess Caitlin is determined not to show up for the next quiz. Yeah, what a drive it's going to be. Well, okay, we know that she's not afraid of snow anymore because there can be okay glaciers on the street, but she'll still make it out. Okay. Good. Yes, my dear. I wish I was able to what the heck can we call it? Be able to fulfill these harsh commitments that I make on Zoom. But there has to be an answer sheet submitted with your signature on it. So, but
Okay, I'll be there.
that's fine. If you're able to answer it today, you'll be able to answer it on the 20 whatever. Okay. So the beam that contains no harmonic frequency sound at the skin surface, thereby avoiding distortion and reduction of noise. Good. Any question, guys? So that was mainly the summary. Yeah, okay. Good. But guys, just take a little while, read on this, chew on it, okay? And no, you guys be willing to be back at 12? For a brief follow-up and just a brief update of the last two topics. And then having somehow ED.
Would we be out by 1? Ish?
Yeah, hopefully. Yes, Lillian. Where is the big smile about?
I'm fine with whatever.
You're fine with whatever. Okay, guys. So, please try to take 10, 15 minutes or whatever you have, 20 minutes to read on your tissue harmonics. And when we come back, should we say 12:05? We just briefly talk a bit about pulse inversion harmonics and even briefly about power modulation harmonics. And see, so here was the disadvantages and advantages of this. That's pretty much it. Okay. A lot of the juicy details, we don't really need to go into all that. Okay. So it's going to be brief. So see you guys at 12:05. Okay, guys? Now, as far as, what can we call it? Harmonics being, well, okay, produced, we just talked about, but okay, how is it that the system? We can say, okay, two technologies by which is okay, the system actually is okay, will use to produce what we call our harmonic images. Yeah, okay, which is going to be as okay as a result of the harmonics frequency, which was twice that of our fundamental frequency. But the system mainly is okay used, we can say it's okay two type of technologies. Now all the juicy details and so on, so on, so what happens and so on, so you don't really need to go into it. Okay. But we just briefly, just briefly mention what these are about. So one is going to be what we call pulse inversion harmonics. Okay. The other one is going to be what we're going to say is will be power modulation harmonics. Yeah. Okay. Now, what is pulse inversion harmonics? Now, what mainly happens here, guys, is that the system mainly will produce a pulse. That's our first pulse along a scan line. Yeah, okay. But the mechanism that applies here is that there's going to be a pulse inversion, which mainly means that it will produce an inverted pulse. What do you mean by an inverted pulse? A pulse that is going to be opposite to the first pulse. So what we actually have is that there's going to be a pulse which will be inverted to it. Did that make sense? Okay, so what we actually have along each scan line is we have an initial pulse, and we have a pulse which is going to be completely inverted to our first pulse. That is what you call pulse inversion harmonics. Okay, did that make sense? Well, probably not. But if you got this much, okay, yes, you should be good. Clear, okay. Now what it mainly is, then talks about, these two pulses here is, are going to cancel out one another. Right? Okay. they will cancel out one another, but mainly because of, we can say as, okay, the only way that I was able to just, okay, make sense out of this is that, okay, as the inverter pulse display as, okay, that nonlinear behavior, where you mainly says, okay, whatever is left behind after, yes, okay, these two pulses, yes, okay, cancel off one another, is as a result of the product of the nonlinear behavior of the second pulse that will produce your harmonic image.
So there's an initial pulse and then an opposite pulse,
Mhm.
and then they cancel out.
Mhm.
And then what are you left with?
Because mainly says, okay, the remaining of the pulse of harmonics. I know, and that's why I say, yes, okay, etchament. Hakuna Matata. Because, okay, listen. We can try to read it together and see if anybody is okay can figure out. So pulse inversion harmonics, what does it say? Okay, is an imaging technique used specifically designed to utilize harmonic reflections, which are distortion-free while eliminating the distorted and fundamental reflections. Good. Okay. Now, reflection contain both fundamental and harmonic frequencies. Now, what were your fundamental frequencies? Frequency equal to that of your transducer, right? And harmonic frequency, what was that? Frequency twice that of your fundamental frequency, whatever that was. Okay. Now, fundamental images would have been produced by the fundamental frequency, harmonic frequency, or harmonic images were produced by the harmonic frequency. Clear? Okay. Okay, good. Now, if you just go down to, yes, okay, the 1, 2, 3, 4 paragraph, because that's where it talks about, yes, okay, we can talk to, say, the original fundamental or pulse inversion technology. With pulse inversion harmonics, 2 consecutive pulses are transmitted down each scan line. Did that make sense? Okay, so what did we have in, or let's put it this way, what did we have in fundamental imaging? There was only going to be 1 pulse per scan line, right? Did you guys get that? But what do we have here? Along each scan line is going to be 2 pulses. Did that make sense? Well, okay. Okay. The first is a typical pulse. Clear? Okay. The second is an inverted copy. Now, what do you mean by inverted? If one is up, the other is down. So if one has the peak, the other will have a trough. And likewise, all right? Okay. Did that make sense? So it's going to be as, okay, an inverted copy of the first pulse that is going to be traveling down the scan line along with the original pulse of first pulse. Just an inverted copy. What does it mean to be inverted? That one has the peak, the other has the trough. When it has the trough, the other has the peak. What does that mean? that they will be outphased, right? And when things are outphased, what do you have? When sound waves are outphased, what do you have?
A smaller final wave.
But here it's a true copy. So the power or the amplitude of the two waves are going to be the same, right?
So then you have nothing.
Nothing. Clear? Okay.
Then there's nothing.
Okay. But so that's what it says. Okay, the second person in a word copy okay, as in a word copy that is out of phase with the first. Whenever a compression exists in the first pulse, there's a rarefaction in the second pulse. Now, reflection from these pulses are combined in the receiver. Since fundamental portions of the reflections exhibit linear behavior to the two inverse pulses, or the two inverse fundamental signals are destructively interfere and completely cancel out each other. That's what I said, that the fundamental pulses will completely cancel out one another. Clear? Okay. Since, or however, since harmonics exhibit a nonlinear behavior. What was a nonlinear behavior? Well, here we can say, okay, that we will have a different propagation speed in compression versus rarefaction. Okay, things like that. Okay, the harmonic portion of the reflections are in phase and will then constructively interfere. So whatever is okay as remaining from the harmonics, which is nonlinear behavior, that will constructively interfere. And what do you have then? Signal. So that's why I said, please keep in mind, okay, I'll just put it this way. Two pulses travel down. That, okay, yes, if they were fundamental, yes, okay, they cancel out one another. Okay, but saying yes, okay, we have harmonics is going to mean yes, okay, just root, yes, okay, we can say it's okay, retrieve, yes, okay, what is produced by the nonlinear behavior of these pulses here to, yes, okay, create a harmonic image. Okay. So the actual mechanism is not really something that you guys need to worry about. Just remember this much, it's 2 pulses per scan line. So what do you have? Each frame, if it was a fundamental image, let's say it's okay, it was produced by 100 pulses because we had 100 scan lines, right? You recall that? Okay. But what do we have here? 2 pulses per scan line. So what do you have? Twice the number of pulses per frame, right? Yes, guys. I draw lines in the sand and say, well, okay, I just want one person running down each of these lines here. Let's say it's okay, we had 10 lines, then there will be, it's okay, 10 people running down and coming back. Did that make sense? Now, if I say it's okay, I want 2 people to run down each line, how many people will be running back and forth? If you had 10 lines. I draw 10 lines in the sand and have 2 people running down each line. How many people will be running back and forth?
20.
20. Okay. But these people running back and forth, what would we consider them? Yes, okay, pulses. Okay, so what do we say now is that we have more pulses per frame. What does that more pulses per frame do? That's going to increase your chi frame. And if chi frame is increased, what happens to your frame rate?
Decreases.
Decreases. I mean, your frame rate decreases, what happens then?
For temporal resolution.
Poor temporal resolution. Did that make sense? So the advantage here is, okay, as we get better spatial resolutions, whether that was, okay, as things like that, axial resolutions, or as, okay, lateral resolution because of less distortion of the beam, right? Clear, okay. But what is it that it does? On the other hand, it degrades your temporal resolution. So harmonics is probably not going to be the best to utilize if you are looking at a moving structure, a structure that changes its place, position, or shape. Unless that movement is so sluggish that, okay, it may not be affected by the increased number of pulses. Okay. But as I say, it's okay, guys, don't go into all that, okay, yes. Just remember this much, that is 2 pulses per scan line. And just as the name tells you, pulse inversion, that these 2 pulses here are, or 1 pulse is just an inverted copy of the other. What does it mean to be an inverted copy? That one is at the peak, the other is going to, the inverted copy is going to have its trough, and so on. Clear? Okay. Did that make sense? Okay. That's all you need. And then, okay, yes, you can say, it's okay, what? No. Go tomorrow. Excuse this. Okay. Sorry. Did that make sense? But though it's okay, you don't really have to go into all the details of, okay, as what's being canceled, what's being this, what's being that. Clear? Okay. Now power modulation, harmonics. Okay. Now what does it have similar to your, okay. So that's going to be as, okay, some similarity to, as, okay, your pulse inversion. Now we say, it's okay, power modulation, harmonics. Okay, now this is mainly as, okay, just another type of, you can say, as, okay, technology that, okay, yes, certain machines may use to create harmonic imaging. Now what is similar between this and pulse inversion harmonics is, well, okay, this one here used 2 pulses per scan line. And that's what we also have in power harmonics. So that's also going to, yes, okay, use 2 pulses. Now the difference here is The difference here is that, okay, here because mainly says, okay, these two pulses here, that's okay, were off. We can say, okay, similar power, intensity, and amplitude. What we have in power modulation is that, okay, we had two pulses, but here it's okay, because it's okay, one pulse is weak. Whereas the other pulse is strong. Now, what mainly is okay will happen, okay, is that this weak pulse here is okay, its power. It's actually going to be modulated. Okay. But again, it's okay, it is as a result of these two pulses here. Again, it's okay, interfering. That is just going to be as okay, what is left after the interference. That will produce your harmonics image. So here's okay, the power modulation, it means okay that this weaker pulse here is, its power is being modulated, or we can actually say it's okay, increased. But it's when these two here is okay, interfere. That okay, whatever is left is going to is okay, of frequencies or sound waves of that interference that actually is okay, will produce your harmonic image. But as we see here as well, that this also is okay, use two pulses. So what did that tell us? That this one here also is okay, will have a degraded temporal resolution. So what was the benefit of okay as using my what the we call it? Sorry, harmonics. You can say it's okay. It improves the picture quality, reduce noise. Okay, we can say it's okay. Improve our resolution, such as spatial resolution, more pulses, right? Okay, per scan line. Okay, improve our axial resolution, improve our lateral resolution, but degraded the temporal resolution. Okay, so the two types of, you can say, okay, engineering programs or hardwares or softwares that they may use can either use as okay, pulse inversion harmonics or power modulation harmonics. Okay, now which of these two here is the most common one to be used when we talk tissue harmonics? Is pulse inversion. So most systems out there will use pulse inversion harmonics to create tissue harmonics images. Did that make sense? Now, whichever method it was, whether it was power modulation or power or just a pulse inversion, you can say it's okay, just as a cheat. There is not only as okay the harmonic frequency, which is twice that of the fundamental frequency, but you can also say it's okay the number of pulses used in harmonics is twice that used in fundamental imaging. Because in both mechanisms, it's okay, what did you have? 2 pulses down each scan line. Clear? It's what happens to those pulses, that's okay. That is different. But even if, okay, if you look at the word pulse inversion charge, it's okay, one pulse, if it's like this, the other is like that. And vice versa. Whereas power modulation, modulating, or yes, okay, modeling or changing the power. And here's going to be, yes, okay, the power of the weaker pulse that is going to be doubled, but the weaker pulse and which is now doubled in its power is going to, yes, okay, again, yes, okay, interfere with the initially stronger pulse or whatever is left after that interference is going to be, yes, okay, what will lead to your harmonic image. Any questions? Anybody want to say anything?
Nah.
Nah. Okay, guys. So let's put it this way. Yes, okay. This is all that I might have been able to offer today. So what can you be asked? What can you be asked? You don't know. You may say, it's okay, this is probably okay. The only chapter where you don't have questions in the exam review. Back of the book. Yeah, okay. So is everybody clear upon what it means to be a harmonic frequency? Good. Just twice what your fundamental frequency is. Clear? Okay. Any questions about tissue versus contrast harmonics? The initial thing, during transmission, during reflection. Clear? Okay. What does it mean to be a linear and non-linear behavior? Any questions about any of that? Good. But then yes, okay, what non-linear behaviors is it that is being displayed during the development of tissue harmonics? That's the main thing you guys would need to know. Clear? nonlinear behavior or nonlinear propagation speed when looking at compression versus rarefaction. Nonlinear development of the harmonics. Initially nothing, then an atom. Right? And then, okay, what we know was that harmonics was distortion free. Didn't lose energy, but mainly it's okay applies, or it's going to be more relevant. It's okay when we talk about it's okay our sound beams. Okay, so that's okay. How does that become a benefit? That sound beam is okay, will not lose energy, and okay, yes, will not have the production of loops. Okay. The two mechanisms was respectively or either pulse inversion and power modulation. What they had in common was it was two pulses that would be transmitted. By pulse inversion, it's okay, they were opposite copies of one another. Clear, okay. And okay, yes. Will cancel out, but due to yes, okay, some nonlinear behavior, just okay, whatever was remaining from that from that harmonics produced by the nonlinear behaviors, okay, produce the nonlinear or the harmonic frequency, which produce a non-harmonic image. But due to two pulses down each scan line, more pulses per frame, increase the G frame, reduce the frame rate, reduce the temporal resolution. Power modulation, again, is okay, two pulses, but here it's okay, they are not going to be inverted copies. The difference between these two pulses here is that one is strong, one is weak. But the power of the weaker pulse is doubled. But it will still, yes, okay, interfere with the stronger pulse. But what we can say is okay, mainly is okay, yes. Remaining of okay, yes, that weaker pulse after it interferes with the stronger pulse will produce your harmonic image. That's all. But again, it's okay that you can say it's okay. It uses two pulses, just like pulse inversion. More pulses per frame. More pulses per frame reduce your chi frame, or increase your chi frame, reduces the frame rate. And when the frame rate is reduced, you have more flickering. Or you can say, okay, there will be a degraded temporal resolution. But we get better spatial resolutions, axial resolutions, and or lateral resolutions. Did you guys get that?
Yes.
Good. So if you just kind of are able to recall everything that I just said in the last 7.5 minutes, you should be more than good to be able to answer your questions.
Mike, we don't have to know any like deeper onto the contrast harmonics or micro bubbles.
Micro bubbles, well, those bubbles are going to be discussed tomorrow. So what we have done so far was only as okay, what we could say as okay was tissue harmonics. Okay, so okay. Now guys, so for tomorrow, yes, okay. What I would recommend that you guys know is okay, what do we mean by the word contrast? Not contrast resolution. What does the word contrast mean? Clear? Okay. Then we can say it's okay, contrast agent. Now, generally speaking, yes, okay, it can be called contrast agent here in this book or in this chapter here. We call, or when we talk contrast harmonics, we will just call that contrast agent a microbubble. Clear? And then take it from there. Okay. By going, says, okay, now since it is harmonics, what is it that it's going to have? It's going to just, okay, display some nonlinear behavior. Now, the major nonlinear behavior that we will see be repeated in contrast harmonics is again going to be as, okay, your that nonlinear behavior displayed in phases of compression versus rarefaction. What we can mean is that how will that affect your microbubble or contrast agent? And how is that then going to create a greater or lesser contrast effect on your image? That will be all. Did you guys get that? Okay, but please make sure that you know the meaning of the word contrast. Not contrast resolution, just the word contrast. Okay. Okay, guys. Now, if you guys don't have any further questions, you are more than welcome to, yes, okay, take your delayed lunch and read. Okay. And I guess I see you guys tomorrow.
See you tomorrow.
Okay, have fun there.
Hi.
Soon as you get